Thank you, Lindsay. Thank you. It's a pleasure to be back at Met and Mat, or whatever it's called now. It's a little further away from where I remember being taught metallurgy by the likes of Trevor Page and Brian Rouse and people like that. Let me first acknowledge the people who made this talk possible. This is a collaborative piece of work. My colleague Praveen Kumar is younger and more energetic, and most of my programs now are with him. And Dipankar Banerjee, who's an expert on titanium alloys. And the others, the ones below, are all PhD students, two of whom are still alive, and they'll be my last two students, and then some postdocs. And I must acknowledge the collaboration, partly with funding in the case of Pratt & Whitney, and the contributions of Deepa Srinivasan, particularly with regard to additively made materials and titanium alloys, and also Bharat Heavy Electricals, who are in the business of making turbines, steam turbines and gas turbines, and of course all the funding agencies that made it possible. Now this talk is really about two things, two aspects of mechanical testing. One is testing small volumes, and the other is the use of cantilevers. Now small volumes come about in many different situations. The first relates to where phenomena change with length scales, whether it's fracture or the yield stress or magnetic coercivity. So the different phenomena that kick in when you go below a certain size. And so you get effects which you don't see in large bulk materials. You also have length scale issues or the need to test small samples when you have coatings or surface damage layers. These could be in thermal barriers or PVD coatings. In the case of these tribological layers that form on railway lines, the mechanical properties of the regions which determine wear or fracture are very small. And so you need to know what they are. Or in the case of a tribofilm on an aluminum silicon piston. So that's one class of systems where you need to find ways of testing small samples. Then there's a whole domain of life extension and repair. So this is a steam turbine blade. And on the right, you have some gas turbine components, which you'll see the damaged one here and how it is rebuilt with additive manufacturing. This is again from the work of people in GE Power and Intech. So you need to be able to evaluate what it is that you've added on, whether its properties are satisfactory and whether they are integrated to the bulk and the interface is all right. In case we think this is all very new, the testing of small systems goes back a long way. And I was preparing an article, and I'd always thought Griffith was the first person to look into this whole business of strength and glass fibers and so on. But about 20 to 30 years before, there's this gentleman called C.V. Boyce, C. Vernon Boyce, I don't know what the C is for, who was testing quartz fibers made by taking a bit of molten silica and firing it out from the tip of an arrow. And so as it flew out, it solidified very rapidly and made very small fibers. And he was able to do things which are quite astonishing for that period in time. He was able to measure the gravitational constant using much smaller objects than Cavendish did in those famous experiments. And if you work out the numbers that he, in terms of force that he was able to measure, he was measuring forces as small as femtonewtons, being able to detect the radiation from the moon, from a candle, and so on. About contemporary with Griffith was also this paper from the Bureau of Plant Industry, some very obscure institutions that did such work, where people were interested in thermoelectric wires, and these were for temperature measurements. And so these were experiments where very fine fibers of bismuth and antimony were drawn. And some of the things we now know very well were understood even then, namely that the strength increased and that the materials exhibited a fatigue limit. That is, below a certain stress, they would not fail at all, stand indefinite bending. The other part of this business is bending and the convenience of bending. I think it's arguable that mechanical testing began with bending earlier than people did uniaxial tension. And this applied to elasticity, plasticity, and of course, creep. And these are two papers from the early 1930s, where they took some enormous lead beams and put strain gauges on them and established certain things. First of all, they established that the strain was linear across the cross-section, even though the stress and strain are no longer linearly related. This is power law creep. They established that after a primary stage, if you look at the strain, it reached a steady state. That is, the strain increased linearly with time. So they were able to recapture many of the attributes of uniaxial creep in a bending experiment. But the catch, of course, was that since stress and strain are not linear, or stress and strain rate, one didn't know what the stress was. So you could measure the strain and you could establish that it's linear, but you didn't know what the stress is. So this is something fundamental to all bending experiments which involve nonlinearity. In uniaxial experiments, you take the load and divide it by the area, and you get your stress. You can't do that here. So here's what's happening. The point 0 is the neutral axis, is the midpoint of the beam. So we're just showing one half of it. And the x-axis is the strain. So when you start, you're predominantly elastic. And so the total strain and the elastic strain are more or less the same. There's very little creep. Now, as you start creeping, the nonlinear part of the deformation becomes more and more important. And so your stress now has to adjust itself because the strain remains linear and therefore the stress can't be linear. So what you have is this phenomenon of load shedding. Namely, instead of the stress being here as an elasticity, it drops. And over here, near the neutral axis, it actually increases. So if you think about it, this is the same phenomenon that you have. So by the time you've reached a large creep strain, where you can neglect the elastic part, your total strain is more or less your creep strain. But the distribution of elastic strain actually tells you the stress. So the stress distribution, of course, is proportional to the elastic strain. Now, this is a very familiar phenomenon. There's nothing very mysterious in all this. And we see this in a fiber reinforced composite. The load is shed by the harder material to the softer material. In a dual phase ferritic martensitic steel, the stress shifts to the martensite, and so on and so forth. This is a case where you have load shedding from a purely geometric effect. Actually, we know this in bimaterial beams. If one half is stiffer than the other, then it'll take more of the load, and therefore the neutral axis will shift to the harder side. And so this is a brief historical survey of the people in bending, starting with elasticity and creep. So after these early experiments, around about the 1930s and up to the 50s, bending sort of fell out of favor because of this nuisance, that is, that you didn't know what the stress was. And people were perfectly happy to do uniaxial experiments, with one exception, namely in ceramics, because in ceramics it's difficult to do uniaxial experiments, especially in tension. So people continue to do bending in ceramics and look at many aspects of deformation, particularly in creep, because there's not much plasticity otherwise. And if you're interested, there's a review in the Journal of Metals about 6 years ago, written by a former student of mine who's now at Johns Hopkins, which surveys this part of the history. So this is an outline of what I'll present. The idea of getting multiple stress-strain rate pairs from a single test. So you replace half a dozen creep tests with one test. Sample thickness effects. The situation where you don't have steady state creep. Namely, there are some systems where you either go into tertiary very quickly or you have a non-steady state decaying creep, sort of Andrade type deformation. And then some more recent things where we haven't really got a full handle on how to deal with it. Situations where you have tension, compression, asymmetry. Bending requires that you have your output comes both from the tensile and the compressive side, whether you like it or not. So where there is symmetry, the analysis is simple. Where it isn't there, if you're flogging this technique, you can say it's a way of getting compression and tension data from the same experiment. But the fact of the matter is it's a problem. If you want tension data, you have to deal with the fact that compression is different. And finally, I'll come to the situation where we have joints, welds, and maybe additively made materials. So given that strain, I will use strain loosely. It's really strain rate, which is proportional to stress raised to some power. The distribution of strain tends to be highly localized with respect to stress, because if I halve the stress, the strain will drop by a factor of 64. And so if I have a cantilever like this, if I go to the middle of the cantilever, the stress is dropped by a factor of 2, and my strain rate will have dropped by a factor of nearly 2 orders of magnitude. So if I have a stress exponent of 6. So here's an example. This is a strain contours using digital image correlation. I think this is from lead. This is in the early days when we hadn't worked out the way in which to paint at high temperatures and so on. So you can get different domains of creep behavior with n equal to 1, 4.5, and the regular power law, and then power law breakdown. And you can see how the strain contours get more and more concentrated near the fixed end. Now, nevertheless, there are certain dimensional relationships that hold. The first is that stress must be proportional to the bending moment, and therefore it scales linearly along the length of the beam. Compatibility dictates that the strain is linear across the cross-section. So you don't know what the stress is across the cross-section, and you don't know what the strain rate is across the length, along the length, but these two must hold. So here's roughly how it works. This is the DIC spray pattern. So what you see on the left is the fixed end of the cantilever, and the load would be applied somewhere on the right. And then as you monitor the strain, you'll see this beam bending. And once you reach steady state, you're acquiring multiple data points across the cross-section here, always orthogonal to the curvature. And you're able to get multiple stress strain rate curves. And if you superimpose the red ones which come from the cantilever on the other ones, which are either blue or black, I can't tell, which come from individual uniaxial experiments, you'll see that you recover the same data. So this is a way of using a cantilever which is all said and done easier to align. You can cut smaller samples and replace multiple tests with one of them. Now that's as far as steady state creep goes. Now, when you have primary creep, we know that the creep rate is changing with time. The exponent that relates stress and strain rate may not be the same as what it is in steady state. But nevertheless, it turns out that when you watch the stress state change from the linear behavior to the redistributed shape, there is one point here at which all these lines cross, more or less irrespective of what the stress exponent is. So by now you'll have got that the shape of the stress distribution across the beam depends on n, the stress exponent. If it were plasticity, it would depend on the relationship between stress and strain, which is the work hardened coefficient. So if you now monitor the stress at this point 2, which is roughly 2/3 of the distance from the neutral axis to the top surface, then you will find that you can recover all these exponents for, this is a representation of the total strain as elasticity plus the primary part and the steady state part. If you look at beam location 2, which is this green thing here, you'll find that you get a very good correspondence with the black uniaxial data, because the stress there effectively doesn't change. And therefore, you're doing a uniaxial experiment at that point. And so by moving along the length of the beam at 2/3 of the distance from the neutral axis, you are getting multiple strain rate curves for different stresses. Now, we thought we'd done something very clever, but then unfortunately the student read the literature more carefully and found that somebody had noted this in 1963. This is Marriott and Leckey. It is in some obscure proceedings. I don't know how she even found it. But essentially, this was an this was a numerical calculation of beam bending, which showed that there were certain points which they call them skeletal points. We call them invariant location. It's all the same thing. So using this, one can do things like use additively made materials when materials are in short supply. I'll show you a bunch of curves like this. They basically tell you that the data you get from the literature and what you get from bending all fall on the same line. But essentially, you're getting multiple stress strain rate curves from one sample. And this is subsequently we got on to higher temperatures. This is a Haynes 282 alloy at 750 degrees. Now let me address something which is a nuisance, namely sample thickness effects. If you're doing science, length scale effects are very interesting, but if you want to generate realistic data, length scale effects impose a limit on how small you can make your sample, because then you start getting information which is no longer can no longer be extrapolated to the bulk. So here's a test. I must thank Anton Parr, who makes these micro indentation systems. At their lab, they had they're very small beams. This beam is about 0.5 millimeter in thickness. And so we needed a facility for imaging and loading, which we availed of at their laboratory near Delhi. So you'll see exactly the same bunch of curves. So this is that beam bending. And there's a bunch of creep curves that you see here on the left developing. Now, when you plot the data, what you find is that the bulk data, bulk means in this case anything above about 3 millimeters or larger, essentially gives you a scale independent behavior. But when you test these smaller beams, you find that there's a strengthening by a factor of about anywhere from 10 to 100. So in bending, small beams are stronger. And we argued that, so here another example, this is commercial purity aluminum. This is 5 nines aluminum, 250, 300 degrees. Again, this top set of data are for what's called bulk, anything which is 3 and above. And here, we're progressively reducing the thickness of the beam. And you'll see very dramatic differences. I mean, in this case, it's probably a few orders of magnitude, 2 or 3 orders of magnitude strengthening that you get from small beams. Now, it turns out that the substructure that you develop during creep is similar to what you have under uniaxial condition. What you get under bending is similar to what you have under uniaxial conditions. So that was established independently. But then when you get to very small beams, you get a much finer substructure of dislocations. And we argued that this is because of geometrically necessary dislocations, because now your strain gradients are extremely high. Remember that neutral axis, the strain is 0, and you have the maximum strain at the surfaces. And so these pump in additional dislocations, which refine your structure and thereby reduce the creep rate. And if you, what the student did here was edge pit the sample from and look at the dislocation density, this is aluminum, from top to bottom. You will see that as you approach the neutral axis, which is somewhere here, the dislocations all disappear. And then when you get into the compressive side, they start picking up again. So you can standardize this. You can normalize it and bring it to a length scale independent or derive an independent parameter, which is shown here, except one doesn't know what H bulk is. So this is a fitting parameter. If you use a certain value of H bulk, then anything smaller than that, you can show scales linearly with the magnitude of that ratio. Interestingly, this is in contrast to uniaxial experiments where small samples are softer. And they're softer because the effect, there are no strain gradients there, but the microstructural length scale near the surface is actually coarser than it is in the bulk because dislocations escape easily from the surface. So this surface affected region works like creates a sort of a composite. You have a soft outer surface and a stronger inside. And so your creep rate reduces as the proportion of surface area becomes larger. So now let me come to the case of titanium alloys where at room temperature, this is a very unusual phenomenon. Titanium is a very refractory metal, but it exhibits a phenomenon of room temperature creep, which is exacerbated by fatigue. And so this is a very important aspect of that contributes to failure. And this is a famous failure. I think it's an Air France plane where the engine fell off. The engine fell off, and this is being recovered from the Greenland ice cap. And when the analysis was carried out, the failure was tracked to in the compressor to the fan, to regions which have a predominant C-axis orientation in the direction of the applied stress. So these are what are called these microtextured regions, which some of you may be familiar with. I think they have largely been eliminated today by changing the deformation process or the working process. But unfortunately, there are a lot of legacy planes which are still flying around and will continue to fly around. And so this is a serious problem. Now, we got into this because somebody paid us money to get into it. But then we realized that this is a very complicated problem. Backed off to look at a simple case of a highly textured titanium alloy, which is shown here, where you have a very strong, it's a roll plate. So the normal of the roll plate is very strongly 0001, which means in the plane of the plate, you're looking at something which is largely in the basal plane. Now, titanium is complicated for many reasons. Apart from creeping at room temperature, it also has tension compression asymmetry. And we didn't want to deal with that right away. And of course, it has this decaying creep. You never reach steady state. So we began to analyze this problem because now we had to do some bit of mathematical analysis along the rolling direction, where we expected things to be symmetric in tension and compression. So just to illustrate, the yield stresses, I'm sorry, you won't be able to read the numbers, but these are on the rolling and transverse directions. You'll see the yield stress is around 700 megapascals. Whereas if you get to the normal direction, the yield stress is about 1100, about 50% larger because of the strong texture. If you try to pull along the C-axis, basically the result shear stresses on slip planes, easy slip planes, very low. You have to activate pyramidal slip with C plus A, Berg's vectors, and so on. So this was the challenge before us: strong rolling texture, anisotropy in yield. Now the question is, what about creep? Bending is ideal here because when you have rolled plate, it's very hard to get samples perpendicular to the along the thickness direction. But we'll start with the rolling direction. And what you find is that it's nice and symmetric. This is reassuring. Everything above the midway point, this is the neutral axis. Everything above here is in tension, and this is in compression. So this is just a creep test at room temperature and measuring strains using digital image correlation. Now, we set about trying to model this exercise. I won't labor this too much, but basically, you're working here at stresses where the material may have yielded. These are extremely high stresses at which creep is taking place, which is very different from high temperature creep, where you're at a small fraction of the yield stress. So we fit the uniaxial behavior, the stress strain curve, the creep curve, and then we use that to predict what will happen in bending. This is the reverse of what we want to do, but this is just to see if what you measure is consistent with what you predict. So remember that when you do a creep test in bending, the stress is changing all the time. At a given point, the stress never reaches steady state. So this is not steady state strain rate, but steady state stress distribution, if you like. So you have to adjust the deformation rate at any point by moving from one creep curve at a stress of, let's say, sigma 1 to a changed value at sigma 2. And this is done iteratively for the entire beam in a self-consistent way, so that you balance the bending moment, whatever load you're applying, and you maintain strain linearity across the section. When you do that, you get a reasonable correspondence between the prediction and the experiment of the deflection. So the only thing you're measuring here is the deflection rate. So this gives us confidence that the model works, which means you can now go back and extract stresses. And if you, because the model includes the stresses and strains at every position. And if you do that, what you find is that, once again, there is this so-called invariant location. Even in the situation where you have decaying creep, you have plasticity before creep begins, and so on. So now we can go back to these locations with the confidence that each of them corresponds to a particular stress, and back out the strain rates, and then compare them with what the uniaxial strain rates will be. And this is what you end up with. I mean, given the scatter and creep, this is not too bad. So basically, you're getting multiple strain rate stress curves between 600 and about almost 700 megapascals from one bending experiment. So this gave us confidence that one could extend this analysis to non-steady state, decaying creep type of situations, but again, maintaining tension compression asymmetry, symmetry. Now you can do this in polycrystalline titanium. So this is a region which has microtextured regions, but we've taken a particular part for the cantilever which doesn't have any of these so-called MTRs. The top is a polarized light picture, and this was a way of quickly establishing whether you have these textured regions. EBSD is a very laborious thing to carry out on a beam. So again, the strain is linear across the section, and you get these multiple creep curves. And from this, you can establish what your constitutive law is in a polycrystalline Chi-6-4. And you can extract these creep parameters. This is below the yield. This is above the yield stress, and this is below the yield stress. These results just came in a week or so ago. I've asked the student to see if we can fit them all into one, but you'll find that the stress exponents and the time exponents of the decay are all very similar. Now let's come to tension compression asymmetry. This is an outstanding problem. It's been dealt with in ceramics, concrete, many materials which creep over geological timescales, but which have inherent porosity. They are by definition almost tension compression asymmetric. And so people have grappled with this problem, and they've recognized, this is from some work on refractories. You'll notice that the original midpoint of the beam is here, but the neutral axis has shifted to one side after a long period of refractory deformation. The problem with most of these analyses is that they assume that steady state is reached, whereas almost certainly because of the asymmetry, the tension side cavitates, and when it cavitates, it goes on creeping faster. When it creeps faster, it sheds more load to the compressive side. So it's a very dynamically evolving situation. And so if you now look at this material, namely the strongly C-axis textured material, you will see that there's a huge asymmetry in the strain, in the tension side, and in the compression side. So in the tension side, you're about 0.55, and the compression side, you're at about 0.2, about a factor of 3 difference in the strain. So this is the problem that we're currently grappling with. Well, we can find a student to continue the work. Because here there are too many unknowns to be able to take experimental data and try to recover a constitutive law. You have 3 unknowns in tension and 3 unknowns in compression. So one has to do a little more work, and this is where we think some machine learning techniques might be of use. Now, what happens if you have these microtextured regions? So here are these microtextured regions. I mean, this shows you the orientation of C-axis along the transverse direction. You'll see they are millimeters in length. These are extremely large inhomogeneities. So clearly, if they land up in either the top or the bottom half of the beam, it should be reflected in the way the beam deforms. And indeed, you can see that. So if you have a soft MTR in the tensile half, the tensile strains are much larger than the compressive strains. If it's reversed, the compressive side becomes stronger than or more deforms more than the tensile side. If the MTR is on both sides, but you're pulling along the C-axis, then the beams are differentiated not because one half has an MTR or not, but because tension and compression are different when you pull along the C-axis. So it's a hideously complicated exercise, and that's what you see in the last, where the tension side has a strain of about 0.2 and the compressive side 0.15. By the way, the difference in strains doesn't look very large, but remember that the moment you have asymmetry, the load sheds. So the tensile side actually becomes less loaded, and so the creep rate falls. And the compressive side becomes more loaded, and the creep rate rises. So the strain distribution always remains linear, which means that the tension and compressive strains can't be very different. But the stresses can be dramatically different. Let me come to welds and additive manufacturing. One of the programs we undertook was to look at the residual creep behavior of boiler tubes. These had been run in steam turbines for up to 27 years. And the question was whether this technique could be used to take very small coupons out and see whether the creep properties had deteriorated. Because depending on what the creep properties were, you could decide to continue the boiler for another 5 years, which is not insignificant, even after 27 years, or whether the tubes had to be changed. So what we did was we cut these coupons out from the tubes. Some we tested as monolithic coupons, and others we additively put a handle of an inconel. So in a sense, okay, this is my cantilever. The portion which is deforming is the steel, which is over here. But the strain over here is more or less irrelevant because the stress drops off so fast that the strain rate becomes negligible. So this can be replaced by an inconel. You just want something which is stiff and doesn't deform. Otherwise, this portion will bend into U and nothing will happen here. So you can reduce the size of the coupon and increase the size of the handle, if you like, the lever arm. So we do different ratios of the two. This is the interface between the inconel and the T22. It's a very small layer. We don't believe it has much of an influence. Anyway, it holds up. There's nothing special going on there. And so one can, again, start doing experiments where you recover the strain as a function of time, except now part of this is your sample and part of this is inconel. So this is what you get. Whether you have a monolithic material or 30%, that is, the length of the cantilever is 70% inconel and 30% sample steel, your data more or less collapse onto the same line. And there is a factor of 7 or 6 or something increase in the creep rate with respect to the virgin material, which was put into service 27 years prior. Now, of course, the interesting point here is how much smaller can you make it? So here the cantilever was, let's say, L. We were working with a sample just 0.3 L. It turns out that you can get to about the beam thickness. That is, you can use practically a stubby coupon where the thickness is the same as the length, and then just add on a long handle of something else. So this is a way of greatly reducing the amount of material that needs to be extracted, which is obviously useful if the component has to continue to be in service while you're doing all these analyses. I'm not going through the details, but what it says is as long as you stay about the beam thickness away from the interface with the weld, you're safe. You recover the bulk data. And so we're now looking at welds, and these are for steam power plants in nuclear reactors, where we have a steel which is bonded to a nickel-based superalloy with a number of layers in between. There's a buttering layer, there's a weld, and so on. And so one needs to know where the failure is likely to happen, which is a sensitive region, and an estimate of what the failure or what the creep rates are in that region. There's an interesting consequence of this load shedding, and I'd like to illustrate that with this particular example, where we have two aluminum alloys. They're made by additive manufacturing, laser powder bed fusion. One is a scandium magnesium alloy, which is extremely strong at room temperature, and a silicon magnesium, aluminum silicon magnesium alloy. So if you look at the room temperature behavior, the black line here is a magnesium scandium, which is much stronger than that of the silicon. But by the time you get to 250 degrees, it reverses. And if you look at the creep behavior at 250, you will find that the aluminum scandium magnesium alloy creeps about 100 times faster. Notice that the stresses here are 30 to 70, whereas in the case of aluminum silicon magnesium, it is 60 to 100. So if you look at comparable stress levels, you're looking at a ratio of about anywhere from 50 to about a few hundred. So now the question is this a way of making a sandwich? Is there a way of making a sandwich whereby you retain high temperatures, you retain your room temperature strength, but also don't pay the penalty when you go to high temperatures? So this is the sandwich that was made. One of them is on top and the other is on the bottom. And then you load it like a cantilever. And if you look at the strain rates, you will of course see that the strain is not symmetric, because now you have two different materials. One side is stronger than the other, and so the neutral axis shifts. But it's the magnitude of the strain rate that you achieve which is interesting here. For the same bending moment, you would have either a very soft material or an extremely hard material. By making the sandwich, the soft material's response has actually increased by about 50 times, simply because the load has been transferred to the harder material. So if you do the finite element analysis, what it tells you is that even though the nominal stress under elasticity would give you, let's say, a maximum stress of 70 or 80 megapascals, because of this load shedding, the stress on the softer side has actually dropped to 30. There's a sharp spike near the midpoint of the beam when you move to the other material, and then the stress goes into compression. But this is and the stress is of course larger. You have to compensate. If you take the load away from here, you have to put it somewhere else. But then that material is intrinsically harder anyway. So the increase in the creep rate there is not very significant. On the other hand, the reduction in the creep rate here due to the load shedding is very significant. So basically, you get an effective almost 2 orders of magnitude reduction for the same bending moment. So this might be of interest, for example, if you have a material like a heat exchanger. This is actually the original idea that the company had, was to use it in heat exchangers, where of course there are strong thermal gradients, and you would need strength and creep resistance over a range of temperatures. So we're currently working with a company. Well, the company is doing most of the work in developing a system which will translate this into a product. Industron came out of Hysotron, but it's now an Indian company, and they have their own products of nanomechanical testing. And so this is one which is currently under development, which integrates cantilevers with digital image correlation so that you can produce multiple load displacement or stress strain results from a single test. I take another 5 minutes?
Oh, you're fine.
Oh, okay. I thought I'd just introduce a topic relating to high temperatures, because this is a direction in which we are moving. that is to extend a lot of the steels and aluminum alloys and so on into very refractory materials like niobium alloys and carbon silicon carbide composites. One of the issues, there are a number of issues in high temperature testing, but one of them is in the stability of these patterns that you use for digital image correlation. Contact extensometry becomes a little problematic beyond a certain temperature. And it's really nice to be able to measure strain without poking around with the sample. So we had to learn, this is all learned the hard way, that so-called high temperature paints don't really last very long. This 500 degree C paint was gone after 1 hour at 300. That is, if you look at the correlation, it's pretty good over here and then gone by the time you. So for creep experiments, you really need very long-term stability. A lot of DIC, even at high temperatures, is done with fracture toughness or stress strain curves. So if you have a strain rate of 10 to the minus 3, it doesn't take you very long to do the experiment. It takes you longer to heat the sample up. But if you're doing a creep test for hours, then you need much better stability. So what we had to develop better patterns which retain their integrity. That's number one. By the time you get to very high temperatures, there are other issues. And I'll show you some examples of problems we've had to overcome. The advantages are obvious. This is what the machine, this is what the machine crosshead gives you. And this is what the DIC gives you about the stress strain behavior. So there are all kinds of displacements happening in your machine which have to be subtracted out. And extensometry runs into other problems. Extensometer breaks every 3 runs and it gets expensive. So there are a lot of advantages of DIC. You get full strain field measurements, and this is the strain contour at a crack tip. So one can do all kinds of things with non-standard geometries. So what are the challenges? The first deals with radiation. Second is heat haze, and the third is chemical reaction. Let me just show you some examples of these. So here is an image. This is a carbon fiber silicon carbide composite, room temperature, 1200 and 1500. 12 and 1500 is invisible because the radiation from the black body radiation completely swamps your detector. These curves show you the variation of the black body spectrum with temperature. But if you introduce a filter, you can see now that you can go up to 1500 degrees and still have enough contrast to make measurements. So that's what most of that instrumentation was, both the illumination as well as the filters and the detection side. The second has to do with contrast variations from emissivity and reflectivity. So you're shining light and some of it is bouncing back. You have a speckle on a substrate and they have different reflection parameters with wavelength. So you get some curious effects here. So the top pictures here show you the contrast at room temperature and 1250 from the same speckle. You'll see here is black on white and here is white on black, which probably means that it vanishes somewhere in the middle. So next comes the effect of the incident illumination power. This is a light emitting diode. This is run at 14 watts, this is run at 1 watt. So the temperature is the same. They're both at 1800 degrees. Sorry, what was that? 1600 degrees. But here it's bright on gray, and here is black on white. So finally, you need a compromise which allows you to do all this. And this is one compromise with respect to the power of the illumination. And the speckle used here was a yttrium stabilized zirconia. So when you go to very high temperatures, the number of materials that you can live with sort of reduces. Heat haze. So the natural convection from a hot surface will cause refractive index changes. And this is a bit uncontrolled. So if you if you have this haze where you have all this hot air rising to the surface, your sample rapidly blurs. Whereas if you use a fan, a light fan, just to maintain some laminar flow conditions past the surface, then you'll see that everything remains nice and highly resolved. So if you carry out strain measurements, and these are strain measurements with no stress. So essentially, it's measuring the background noise in your system. You'll find that with the heat haze, you have all these fluctuations, but with the laminar flow, you have a nice horizontal line, which is practically zero. So you have to do this if you want the highest strain resolutions. The last, of course, is delamination and reaction. I mean, we used alumina, and in one case, there was a surface layer of silica, and the alumina and silica react. There's not a whole lot you can do about this, except you have to be sensitive to the paint that you use, depending on the sample that you have. So using this, we were able to carry out thermal expansion measurements. So this is for niobium alloys. So you'll have one set of curves, which is from the literature, and one from the DIC measurement. And this is carbon fiber silicon carbide. So you'll notice there's a reasonably good correspondence between what we're measuring. And so this is this one is at least 1800. It's probably higher because some thermocouple made of platinum melted along the way. So, but the student sort of be conservative in saying it's about at least 1800, but it's probably around 1900 to 1950. With an niobium, of course, you can't go that high. These measurements are made at 1500 degrees. So the strain measurement capability is there. And I'll show you an example of a test. This is now a mechanical test using this digital extensometer, if you like the DIC as an extensometer. So we're not measuring spatially resolved strain here, like in bending. We're just looking at the pattern between the top and the bottom of the gauge length. And in fact, one of the things that allows us to do is to take smaller gauge lengths, because you don't get uniform temperature, shall we say, a reasonably acceptable plus minus over what the company thinks is a constant temperature zone. We actually find that we can only take a smaller region in order to get reliable data for, let's say, plus or minus 5 degrees. You use the extensometer, and what the manufacturer gives you, you're at plus or minus 10, which is okay if you go by ASTM standards, but if you want precision, it may not be okay. It depends on how sensitive your deformation is. So this is a fiber reinforced material, and the strains are not very large. You get up to about 0.3% or 0.2% when everything breaks. Just continuing on this line with regard to high throughput testing. Well, high throughput is really a big basket. There's temperature, stress, and strain. So we've looked at strain and stress here so far. But here's an example of where you can get multiple creep curves from different temperatures. So here, the grips are heated by passing current through them, and the sample is in the middle. So if there's a small temperature gradient between the ends in the middle. So I've got it the other way around. The grips, the current is passed through the sample. The grips are not heated, and so the cooling is from the grips. So the region near the grips are actually slightly colder than the region in the middle. So this is 160, and the ends are at 145. And so again, it's a creep measurement. So you can now measure creep at different temperatures. You can plot activation energies. And one of these curves is from a single experiment with multiple temperatures, and the other one is from individual tests done at half a dozen different temperatures. So if one can integrate bending and temperature gradients and everything, then it would be a way of extracting a large amount of data from one experiment. So I'll just leave you with some closing thoughts. This is a very versatile technique. in a sense, it's been rediscovered after about 90 years. But I think with modern imaging methods and particularly machine learning, you have a large amount of data. Actually, the students now use all the data that they get because you're acquiring strains at every few minutes or seconds, and you have position-sensitive strain measurements over millimeters with about 50 micron resolution. There's an enormous potential to use machine learning methods to extract constitutive laws. Except I don't know anything about machine learning, so somebody else has to find a way of implementing this in practice. So is it really ideal for quickly screening new compositions, the effect of heat treatment, additive manufacturing where you can't make very large samples easily, life extension, and of course things like tension, compression, asymmetry. Actually, bending is very nice for doing compression tests. If you look at a lot of compression tests done under uniaxial conditions, the results are very unreproducible. There are all kinds of issues with friction and alignment. This gets rid of all that. Because where you're applying the load and where you're applying the deformation are two completely different places. So in principle, you could do this in 3 or 4 point bending as well, except the sample volumes will be larger. And in 3-point bending, you're measuring strains, directly below the loading point. Whereas here in a cantilever, the advantage is the loading is here and the deformation is happening there. And very rapid analysis of graded systems like you have in welds and so forth. So with that, I'll stop. I think I'm done. Thank you very much. Thank you for your attention.